All right, hello. Let's do an example of a flow on a line. And the example we're going to use, let's take a mass that's released. It could be released from rest, why not, over the ground. So say V0 is 0 meters per second. Now this is going to experience, if it's fairly close to the surface of the Earth, say within a couple miles, a force of gravity, right? So if we choose positive y down and positive x, say to the right, then we'd have m, g, j hat. You don't have to use the vectors, but why not? And now let's put a dissipative force in. Let's put air resistance in. So this is gravity. And let's do a resistive force, and that's going to be minus CV j hat. Minus, not because it's pointing necessarily upwards, but minus so that it opposes the sign on velocity, the component of velocity. So then, Newton's second law, let's sum the forces. In the y direction, they're not going to be 0. It's going to be my double dot. Double dot means 2 time derivatives. And that's going to be equal to mg minus cv. Okay. And let's also make a couple of notes on units. C must have units of kilograms per second. Notice that I'm using whatever, kilograms, meters, and seconds as the standard metric units most of the time. So when we go through and divide by m, I have y double dot equals g minus c over m v. This thing here will have units of 1 over seconds. Now, we're not solving this analytically today. We will in the near future. And this will have some roll of time. This is a frequency right now, or the flip is some other period, perhaps. So we'll talk about that later, but it's good to keep an eye out for units. Speaking of units, notice that everything works out here. The second derivative of position is meters per second squared. The units of the acceleration due to gravity is meters per second squared. This is meters per second times seconds. So this whole thing is meters per second squared. Everything jives. Now this looks like a second order equation, but we can rewrite it. Y double dot is V dot G minus C over M V. So now we have a first order linear differential equation. Right? It's first order linear differential equation. And because there's no explicit dependence on time, we can graph this like we did in class today. Let me adjust my camera. All right, so what does this look like? Well, it's a linear equation. It's linear in V. So if I graph V dot versus V, I have a line, C over M, it's both positive. So the minus sign tells me it's a decreasing slope. It's a negative slope, rather. And this G is positive 9.8, so it's going to cross up here. So the equation, the graph of the line looks something like that, where this is G, that's the initial acceleration. V dot is acceleration. It's initially G, 9.8. It's not going to be eventually, though. We can find the coordinates of this point. This is when V dot is 0. So that is a velocity of mg over c. So at this particular speed, there's no acceleration. That's interesting. This is an equilibrium. What kind of equilibrium we will find out in a minute. So if you are starting from rest, what happens? You have a positive acceleration, so you speed up. Your acceleration decreases because there's a resistive force, but it's still positive, so you're still increasing the magnitude of your velocity. What happens if you start with a velocity that's greater than mg over c? Then your acceleration is negative. You decrease. And you decrease less and less as you get closer and closer to this equilibrium. What does this look like? Neighboring points are drawn inwards. That's stable. This is a stable equilibrium. And in fact, you've probably heard of this before. It's terminal velocity. So when you jump out of an airplane, and if you do it high enough, at some point you stop accelerating. You're in equilibrium between gravity and air resistance. We can use this to sketch solutions, even though we can't solve the differential equation yet. So let's do that. So and let's put maybe mg over c right here. That's one valid solution. If this is your speed, then it'll stay there. Now if you start from rest, you're going to have a large initial acceleration, or 9.8 anyway, and then it's going to decrease. So that means the slope of your solution will start steep and then decrease towards 0. If you had started with some downward speed, some downward velocity, then your initial acceleration is less than g, but still decreases. So maybe like that, and so on and so forth. If you have an initial speed that's greater than terminal velocity, then it decreases, and the further you are away, the steeper that curve is. That is, the larger the initial acceleration. My bad, actually. I should have said this is v versus t. So we're graphing v of t curves here, depending on an initial condition. These are all possible solutions to the differential equation. And they don't have any inflection points. And this is the stable equilibrium. This is terminal velocity. So there's an example of a differential equation. We can sketch solutions. We can say things about it. We can say that the limit of the velocity as t goes to infinity is mg over c. Okay. So this is all qualitative. Okay.